Hi, this is Olivia Stodig, and this is the third video in the Parametric box model series relating to the code updates in version 003. As last time, you can find the latest code on GitHub at the address below. So the updates in this version relate to three different topics, really. In the first update, we've got some results checking and some model updates to ensure that we calculate the right data. We're also then modeling a wing with multiple sections, and we can include some core in this model as well. And as a final update, we have added some design optimization to the code, and I'll be going through how to use design optimization, first using a simple example and then optimizing the wing model. So this video will cover the first two sections. So checking the analysis results. If you ran the parametric study last time around, you will have seen that there was some positive fiber angle rotation values here. So we are actually looking at rotating the fiber direction of the composite materials on the skins forward only in the previous study. Here I'm running this using negative and positive values to check whether we are actually getting this bend twist coupling effect that we were talking about. And the surprise here is that we're not actually getting it. So something went wrong in our model definition. In fact, what we expected to see was these rotations to become positive as we have negative rotation angles of the material. Now, why are we not getting this? There could be several problems, and in fact, I will show that we have both of these in our analysis in the last version. So the first one is that we are maybe not making the right modeling assumptions compared to what we want to analyze. And the second one is that there's actually some problems with the rotation calculation. So both of those can be fixed, and I'll be going through the steps related to this in the next few slides. So the first one is modeling assumptions. So we know that we're modeling our wing using shell elements, and in Calculix these are 8-node quadratic shell elements, and the order of the nodes here is important because it defines the shell normal. And the shell normal is what is used to project not only the material properties, but also what is used to convert our shell element into a 20-node solid element internally by Calculix when it does the analysis. So getting this orientation right is very important to what we're actually simulating. So in our previous version model, we assumed that we had a continuous surface around the airfoil section here. And that meant that in practice, we were numbering the shell elements so that we had a shell normal that was pointing downwards on the top skin and upwards on the bottom skin. So all the normals were pointing into the wing surface. The effect of that on the material orientation is maybe not what we expected. So here we have a material orientation ORI 0 that we used to orientate the main fiber direction of our composite material along the X direction, which when that is set to 0 on the parametric study, that's just aligned with the span of the wing. And that means that when this orientation is projected onto our surfaces and respecting the shell normals, then we have a Y direction that is pointing aft on the top skin and forward on the bottom skin. And that's equivalent to actually having a continuous piece of composite ply that we're wrapping all the way around on our skin. And maybe that's what we want to model. However, if that's not the case, if we actually want to have different materials or shell sections on the top and the bottom, which is often what you do, you might have a joint here at the leading edge and a joint at the trailing edge. then we might want to actually have two different surfaces, because the problem here is that if we have a continuous surface, we cannot actually induce that bend twist coupling that I was talking about last time. That means that if we are rotating our main fiber direction by a certain angle on the top skin, it does rotate in the opposite direction on the bottom. And that means that we're never going to get this positive or negative bend twist coupling. So what can we do? What we need to do is change the orientation of the shell elements on either the top skin or the bottom skin so that they're consistent. And then we will see that if we apply this rotation angle, then it will be applied in the same direction on both the top and bottom skin. So this is what we want to achieve. Okay, so let's have a look at how we actually implemented this in the code. So there were a few little changes that we did in the parametric box model Python script. So particularly if we look at our get geometry function. So here we have our get airfoil from file. And if we look at that function, we can now see that we're extracting a leading edge index, and that is captured in the output of that function. And on top of that, when we run our getCGX input file, so if we go to that, sorry, it's the one before that actually, it's still in the get geometry function. We have some updates here to the getCGX points and to the getCGX lines 3D, which allow us to extract some split points and some arrow surfaces that are flipped. So what I mean here is that we can actually tell CGX to flip certain surfaces after we've created them. And that allows us to also flip any elements that are associated with those surfaces. So if we look at our CGX file here, it will look very similar to what we had before. The only difference here now is that we are generating 4 sequences. So we actually have 4 splines in our wing model. So that's 2 splines per airfoil section. And we also create these 2 surfaces. So we have one surface that's on the top and one surface on the bottom. And on top of that, what I was just mentioning is that we have this flip command here, which is if you run this after you've actually generated the mesh, then this will flip the elements associated with the top surface as well. And we can check that if we open up this file in CGX. Okay, so this has loaded. Just bring this over. Okay, so this looks very similar to what we had before, and in fact, geometry-wise, it's exactly the same thing. We are enforcing that one node at the leading edge. And if we look at, you can see here, it's not very clear, at least not on my screen, but there is a slight difference in the gray tones. So we have the top skin, the top gray colors are lighter than the gray colors from the bottom here. But if it's difficult to see this, if you toggle the culling back front, now you can see much clearer that this is, if this is appearing as transparent, this is actually the top surface of the shells, and the bottom surface is this dark gray. And if you want to see the mesh, we can switch that on. Element edges, there you go. So you can see that we've got the same sort of mesh that we had before. And on top of that, we can now also check the element numbering. So if I just type plus NA all and execute that in CGX, then we can check that the numbering of the nodes is as we expected. So this is 1425, 1424. We can obviously, this doesn't mean anything on its own, but you will have to look at the mesh file, so the mesh, the all.mesh file, and the definition of the node numbers in the element will tell you whether this shell is has a normal that points up or down. But what we would find if we did that is that both the top skin and the bottom skin are orientated in the same way with the normals pointing up now. Okay, so we've solved that problem. We can now actually implement the bend twist coupling behavior that we expected. Now, the second thing that we wanted to check is that we're calculating the rotation correctly. And actually, if you tried to just correct this model updates that we've just gone through, and you run the parametric studies again, you would still find that you get negative rotations for positive rotation, for negative rotation angles of the material. So something is still wrong. And what happened here is that we weren't calculating our rotation correctly. So in the get average rotation function, we had an origin node that was at the origin of the model. So we weren't actually calculating the rotations around the section at the wingtip. We now have implemented here this leading edge node as our rotation reference point. And this, as you will see, will give us the right results. So here, this is a calculation check, and the best way to check whether this is giving us the right results is to actually implement a test. So we were talking about tests previously. There is now a file called test parametric box.py. And this is an example of a test script. At the moment, it really only implements one very basic test, which is related to testing this get average rotations function. And what we do here is that we're using the PyTest library to parameterize our inputs to this function. So in a separate folder, we now have test data. And in this test data rigid body rotation folder, we have sample CCX outputs where we enforced a rotation, rigid body rotation on the model of a certain value. So here we ran CCX. Here's an input file example if you want to have a look at it. Basically, we changed the boundary conditions here at the root to only just fix one node in 3 degrees of freedom, and then we applied a rotation boundary to all the other nodes in the model, and that results in a rigid body rotation. And so we generated these standard DAT output files. And in our test function, what we do is that we provide a combination of this output DAT file and the rotation that we applied. And we check that if we read our rotations from the DAT file using our standard get average rotations function, we do get exactly or very close to the rotation that we applied in CCX. So to run this, the easiest is to simply run, if you're using VS Code, you can run this using the testing toolbox. You can also, I believe, just run it in a normal PyTest environment. But here to show you what this does is if I launch this test sequence, then all of the tests, all of these parametric tests get executed. And hopefully, if our asserts are all satisfied, we should see this showing up with green ticks in just a second. So all the tests passed, which means that all of our asserts here were correct, and therefore we know that we're calculating our rotations correctly. So now that we've satisfied all of these requirements, we can rerun our parametric study. And here I've done this already, just to speed things up a little bit. What you can check for yourself is that if you run this parametric study again with negative and positive angles, you should see these rotations going from positive values down to negative values down here. Okay, so we've got that topic covered. The next thing I wanted to quickly talk about is some updates that allow us to model multi-section wings with also core-filled sections. So if we look at our parametric box.py file, this relates to a new input that we have at top. So we've already had these two before. So we had our standard Nastran model analysis. We had our composite model analysis in CCX. And now we have this new analysis, which is a model analysis in CCX using a multi-section wing. So here we have the span and the chord that are now specified at multiple positions. In fact, what these values are is length of span along the wing. So we're starting from 0, then incrementing by 8.5 centimeters, incrementing by a meter and almost 2 meters, and then incrementing again by 8 centimeters at the tip. So this allows us to model a wing with 3 sections, 1 section at the root, 1 section at the tip, and then the rest as another section between the two. We have a constant chord for all of these 3 sections. And then we specify that we want to have a filled section here at the root and at the tip, but nothing in the middle of the wing. So this script is an extension of what we had previously. And you will also see that we have some additional element numbers here for the meshing around the airfoil section. That's because now we have 2 cuts in the airfoil. So we're actually defining a cut at the leading edge at 5% from the leading edge along the chord and at 95%. And this allows us to then model these solid elements between these 2 positions. So here we have the number of elements along the airfoil. So this is going from the trailing edge at the top of the airfoil over the leading edge and then back to the trailing edge bottom surface. And these are the number of elements along the span. So we have the number of span-wise elements at the root section, the middle section, and the tip. Otherwise, this is very similar to what we had before. And if we want to see what this model looks like, we can set our inputs to 2 down here and execute that. Okay, so the main process is completed here. We're not actually extracting output from this model because it's a normal modes analysis. So we could just write some code to read the output, but that's not available at the moment. So if we have a look at the output manually, we can actually look at that file first. So we have a CCX normal modes.dat file. That is the output. And what you can see here is that we've got these this frequency output. So we've got the first 10 modes. This model is actually a free model, so it's not constrained anywhere, which means that the first 6 modes that we're getting are very close to having 0 frequency, which is because they're just rigid body modes. And then the 7th mode is the first flexible mode. If we want to actually look at what this looks like, so we can actually open our model using CGX. So this is not static tip shear anymore. This is now CCX normal modes. And this is the model that we've ended up with. So we have the output here for the 10 first modes. So we could look at our mesh first. If we look at element edges, right? So we can see an extent of the root section here, which has a slightly refined mesh with 4 elements. Then we've got our middle section, and then we've got another outer wing section. And if we zoom in, we can see that we have these solid elements now. That are still covered by a composite skin. In this model, it actually does generate some shell mesh on these rib surfaces as well. So that's spurious shell elements, but we're basically setting these properties to have the same stiffness as the core, so they're not actually contributing very much to the model at all. And if you zoom in here, you can see that this the solid mesh actually only extends 4 elements into the depth of the wing. Okay, and finally some results just to have a look at it. So our first flexible mode is mode 7, so we can display the deflections here. And we want to view entity, let's view all. So what we can see here is that the big deflections actually happen on the lower skin. This is a asymmetric airfall. So it's the big flat surface where we have our first bending mode, 20 Hertz. So there you go. These are the main updates to version 003. And the next video will be covering the optimization of the wing model. Thanks for watching.